Okay, to wrap up our discussion about multivariable integration, we're going to do a simple problem. Now, due to the length of multivariable integration problems, I challenged the viewer to try to think of complicated problems for themselves to practice on so that they are more familiar with the conversion as well as why we would exploit symmetry to our advantage. Here in this situation, this is just a simple triple integral with three independent variables in Cartesian. So first we have 0 to 1, 0 to 1, 0 to 1. The viewer is free to choose any parameter that they like, except I just chose these for simplicity. So over here, we have x squared plus xy plus z cubed xy dx, dy, dz. Now, the way we evaluate our integral is from inner to outer. So we have to integrate this 3 times, as given below. Okay, so first, let us look in the innermost one. 0 to 1, x squared plus xy plus z cubed xy dx. In this situation, and similar to partial derivatives, when we are integrating one parameter, all the other independent parameters don't matter. So in this situation, we care only about integrating wherever there is x. So in this case, we have 1/3 x cubed plus 1/2 x squared y plus z cubed y, or apologies, 1/2 z cubed y x squared. And this is evaluated from 0 to 1. If we plug in 0, all of these disappear. If we plug in 1, we get 1/3 plus 1/2 y plus 1/2 yz cubed. Okay? And that's what we then integrate next. So we integrate from 0 to 1 of 1/3 plus 1/2 y plus 1/2 yz cubed. In this case, after dx becomes dy. So we have dy as given below. Here we have 1/3 y plus 1/4 y squared plus 1/4 y squared z cubed, evaluated from 0 to 1. Similarly, if we plug in 0, all the terms disappear. If we plug in 1, we get 1/3 plus 1/4 plus 1/4 z cubed. Here we can combine these and we get 7 over 12. 7 over 12 plus 1/4 z cubed. This is our last one to integrate. So we have the integral from 0 to 1 of 7/12 plus 1/4 z cubed dz, as it's our last parameter. So over here we have 7/12 z plus 1/4 z cubed, or whoops, apologies, forgot to integrate. We have 1/16 z to the 4, evaluated from 0 to 1. If we plug in 0, similarly, all of them disappear. We plug in 1, we get 7 over 12 plus 1 over 16. And this right here becomes our results. We can simplify it if we like, but that's our results. Now, a challenge for the viewer. Try the same problem, but different boundaries. different boundaries. Or try to use cylindrical symmetry. Try to use cylindrical symmetry or spherical symmetry. These are just some variants of how we can do these problems and how we can show how these problems are helpful for us to try and get the best practice out of triple integrals or even double integrals. In general, due to the length and due to the nature of multivariable integration, often these problems take a while to do. So perhaps the best thing we can do is maybe try out the same problem, but different boundaries, make sure you can use cylindrical symmetry, or if you can't, maybe kind of reason why, use spherical symmetry, and maybe reason why you can or can't use it. I hope that this example at least kind of shows how we can carry out the multivariable integration process and how, similar to partial derivatives, that we care only about one parameter at a time. Next, to wrap up the multivariable integration series, we're going to talk about the applications of multivariable calculus or multivariable integration and as to why they would be used just in general. Thank you.